Hi everyone, this is your first video for chapter 4. We're going to start talking about statistics. It's part 1 out of 4 parts. Let's get started. You've heard me say a couple times already that there is no measurement without uncertainty. Every experimental measurement you make has some sort of random error associated with it. Statistics is a tool that we use to help us accept results that have high probability of being correct, so really certain, and rejecting those that are not correct, basically those that are high in uncertainty. There are some basic statistical tests that we're going to talk about, one of them being the method of least squares. And just as a reminder, because we did say this already, statistics only deals with random error. That's very important because we've already, like I mentioned in the last video, we assume that you have detected and corrected determinant error. So you have to be always very vigilant to make sure that your systematic error is dealt with. All right, let's move on. What I'm showing you here is a bar graph of the lifetime of a hypothetical incandescent light bulbs. So obviously you have the number of bulbs as a function of lifetime. And that curve that is superimposed over the bars is what's called the Gaussian distribution. The curve has the same average, standard deviation, and area as the bars. When you see a Gaussian distribution, you have to be able to understand what is going on here. The most probable response is going to be at the center of the curve. And the probability of observing other responses actually decrease as you go away from the center. And the more repetitions you actually make, the closer the bar chart actually gets to the curve. But in real life, that would probably take a huge amount of trials, and that isn't reality. We can't do that. So we suffice with something like maybe 10 trials, or a typical is something, at least 3. You have to have at least 3 trials to be able to get any type of statistic, but that's really low. So I usually, when I do measurements, I do at least 7. Obviously, the more you do, the better. How is a Gaussian curve described? Well, all you need is the average and standard deviation. The mean, or in other terms, the average, is the center of distribution. The standard deviation measures the width of distribution. So how far away is your measurement from the center? The graph that we just saw, would you be able to tell me what the mean is and the standard deviation if I just asked you right now? Well, these are the ways that you calculate mean and standard deviation. The symbol for the average is an X with a bar on the top. That's actually a mathematical symbol. When you see that, that means an average. And you see here it's the sum of all individual data points divided by the total number of data points. So that's a normal average, which most of you already know how to do that. Most of you should already know how to take a standard deviation of something. So all you do is take the sum of the difference of the data point minus the average and square that, and then you divide it by n-1 data points, and you square root it. You should have a standard deviation and a mean button in your calculator. If you don't know how to use it, you better figure it out, because that will save you a ginormous amount of time doing these problems that you're going to do on your exam. So what is the mean and standard deviation in the previous bar graph? Well, it actually told us the mean is 845.2 hours. So on average, these incandescent light bulbs lived that long, and the standard deviation was 94.2 hours. So that's the width of distribution of all of the different light bulbs that they actually tested. What would happen to that curve if the standard deviation was doubled for the same number of observations? What do you think would happen? That curve is going to get shorter and broader. It's going to become less reproducible because you're going to have way more distribution. The smaller the standard deviation, the more precise, in other words, the more reproducible your data is. In real life, we're going to take a limited number of samples when we do an experiment. But for argument's sake, what if we took an infinite number of samples? For an infinite set of data, the average now becomes a population average. Basically what we like to call the true mean, because as you approach infinity, your answer gets closer and closer to the truth. So if you had an infinite number of samples, now that average, which is the x with the bar, now becomes another symbol. The x becomes mu, which is called the population mean, and the standard deviation, S is for a limited sample, but when it approaches infinity, it becomes sigma, which is called the population standard deviation or the true standard deviation. So this is all that's changing, is that as we approach infinity, now these symbols turn into different symbols because they're actually approaching the true value of the measurement. Remember, we can't ever measure the true mean or the true standard deviation because it's infinite. We can't take an infinite number of samples. So you can't ever measure that. But the values of a normal average and a normal standard deviation actually approach mu and sigma as the number of measurements increase. So obviously the more number of samples you take, the better it is because you're approaching that infinity number and that true population mean. So when n is small, when the number of samples is small, the sample mean, the sample average, differs from the population mean. And of course, that's because the small sample of the data doesn't really represent the population. But the difference starts decreasing really, really fast as the number of measurements increase. As a summary, the sample mean is the average of the limited sample. The population mean is the true mean for the population. We can't ever measure the true mean or sigma, the true standard deviation, because it's infinite. It would require an infinite number of samples. All right, let's move on. There are some other terms that you need to become familiar with if you're not already. There's a term called a median. That's just the middle number in a series of data points. So for example, if you had something like 8, 17, 11, 14, and 12, you would put them all in order and then you'd figure out which one is the number that's in the middle. Now this has an odd number of data points, so it's easy, but what if you had an even number of measurements? Then you would take the average of the two middle numbers. So that's what the median is. Don't get it confused with the mean. The mean is the average. What about range? Range is obviously your range of measurement. So if you have something that's really high, you take that and then you take your lowest measurement and you subtract the difference and that'll give you your range. So 17 minus 8, for example, your range is 9 units. In your standard deviation equation, you have that n minus 1 on the bottom. That quantity is called the degrees of freedom. And your book explains it quite nicely. It's initially you have n independent data points representing n pieces of information. But after you compute the average, after you actually make that calculation, there are really only n minus 1 independent pieces of information left because we actually already calculated the average from the n data points. So n minus 1 is how many degrees of freedom you have in your calculation after you've calculated your average. The square of the standard deviation, or S squared, is called variance. Sometimes they ask you for this in certain problems, so you just have to remember that variance is just the standard deviation squared. When they talk about coefficient of variation or a relative standard deviation, these things mean the same thing, okay? So more than likely, I'll probably call it relative standard deviation because it's a lot easier to remember. All that is the standard deviation expressed as a percent of the mean. So 100 basically times standard deviation divided by your average. That is what relative standard deviation is. All right, let's move on. So what's the probability of your data falling within a certain region in this Gaussian curve? It can be shown mathematically that regardless of how wide your distribution is, 68.3% of the area of that curve lies within one standard deviation. So that's that shaded region that you see in the graph. So what that means is that 68.3% of your data points is going to lie within one standard deviation of the center. 95.5% of your data points are going to lie within two standard deviations of the center. And then 99.7% lie within three standard deviations. Another thing you have to take note of is that Gaussian curves are symmetric. So if, let's say, 4.5% of measurements lie outside the range mu plus or minus 2 sigma, then that means that 2.25% of measurements are above, so the mu plus 2 sigma, and 2.25% are below, minus 2 sigma. So now we've learned what a Gaussian curve is, how to describe it, and we've also learned certain terms like median and relative standard deviation and range, all of that. And we've also learned about standard deviation and the probability of your data points being within a certain range in the Gaussian curve. What if I wanted to compare standard deviations? How would I do that between two different sets of measurements? Let's talk about that next. To compare the standard deviations of two sets of measurements, we're going to use the F-test. And here I'm showing you the example that's used in your book. Apparently, trainers inject sodium bicarbonate into horses prior to their racing to neutralize the lactic acid that accumulates in the horse's body, which is awful. But in an effort to try to ban that, they make these instruments, which they don't say what instruments they are, but they make these instruments to try and detect the amount of bicarbonate in the blood of racehorses. So they're comparing two different instruments right here. And you can see that the means are almost the same, but are they significantly different? We have to make sure. This is analytical chemistry, so we're just not going to guess and say, well, yeah, they look close. No, you have to actually prove it mathematically. So we're going to use the F-test. F calculated is equal to the square of the standard deviations, which I remember I told you that was called the variance. So the variance of the first measurement divided by the variance of the second measurement. You always put the larger standard deviation in the numerator because you want your answer to be greater than 1, obviously. So that's how you know what to put on the top. At the end of the calculation, if the F that you calculated is greater than the F in the table, then the value in the table, then the difference is significant. So those standard deviations don't really relate to one another. Now, what table am I talking about? Well, it's on page 81 in your book, but I have it here as well. So let's try to do the problem. You can see that the original instrument is 0.28 standard deviation, so we're going to put that one in the denominator. So what we're going to do is we're going to take 0.47 squared divided by 0.28 squared, and that is going to give you 2.82. So that's the calculated F value. Now let's figure out how much is in the table. There's 4 measurements in S1 and there's 10 measurements in S2. But remember, we have to take it as n-1. These are degrees of freedom. So if your S1 had 3 values, then you would go to this column right here, and then you would go down to number 9 because your S2 had 10, but n-1 is 9. So you see that the F calculated would be 3.86. So as a matter of fact, your F calculated is lower than your F table. So that means that those standard deviations are actually not that different. They're not significantly different. So we can be confident that the new instrument that they're using to test the bicarbonate in the racehorse's blood is as valid as the original instrument that they had validated a long time ago. Alright guys, that's it for this video. We're going to continue with part 2 of statistics in the next one. See you later.